But no, it is okay.
So, Sergei,
Yes,
please begin. We look forward to your talk.
yes. First, I would like to thank Melvin Nathanson uh, mm, for this wonderful conference and for the opportunity for me to attend it. It is really an interesting and high-level meeting. Uh, uh, Recently, maybe a few days ago, a paper by Peasant, Rudnev, and myself was published, and it is a paper about the number of angles formed by endpoints in the plane, and I learned this problem at some CANT meeting. Yeah, and also I published several papers originated from the CANT meetings. But today I will talk about some problems. I heard about them from my former student Mikhail Gabdulin, who gave a talk yesterday. You see that I'll talk about the results represented in 3 papers. The first one was the paper by Gabdulin. The next was our joint paper with him, and the last paper, it is not published yet in a journal, but you can find it in archive. It is our joint paper with Garaev. Okay. Now let me recall some notation. By E of U, I denote the exponent. We consider trigonometric polynomials. This is linear combinations of a finite set of exponents. But here A can be an infinite set. Moment. Yeah. Yes, okay. Now let me say about lambda p set, where p is a number greater than 2. So by we don't know the LP norm of any function, and for example, for any trigonometric polynomial by such a way, the norm f in LP. And if A has the property that for any polynomial with frequencies in A, we have this inequality, so the constant doesn't depend on f. It can depend on p and can depend on a, but doesn't depend on f. Then we say that a is lambda of p set. Well, it is easy to say that if a is lambda p set, it is a subset of the set of integers that it cannot be very large. So the intersection of the set A the segment minus N must have a cardinality at most some number times n to the power 2 over p. Well, but I don't know what to do because I don't see, uh, you don't see the last line. What happened there?
We do, actually.
So the last line is not demonstrated here.
No, we see it.
You can see it, I don't know.
Там мы видим.
I doubt that you see, but let me see that what is on the last line on this page. Bourgain proved that this estimate is sharp, so there is a set A such that A is a lambda p set, and for any n, the number of elements in n has the order n to the power 2 over p. So first, some conjectures about squares. But let me start from the well-known fact that the set of squares is not a lambda 4 set. So the L2 norm is the square root of the sum of squares of absolute values of coefficients, so it is square root of n, and it is noted that L4 norm is greater than n to 1/2. It is n to 1/2 times a logarithmic factor. Sorry. One moment, just again, I don't see the lowest part of this slide.
It's all is fine.
Oh, okay, maybe fine. So that anyway. So can you see for any finite subset B is the subset of Z, the number is equal to what? Can you see it?
Yes.
Yes,
No.
yes, stop.
Yes. You see. Okay. Okay. So it is a well-known conjecture by Rudin that if P is less than 4, then the set of squares is a lambda P set. Let me note that if P is greater than Q and Q is greater than 2, then any lambda P set is also lambda Q set. But our set is not lambda 4 set, and we don't know if it is a lambda P set for P less than 4. And it seems that the problem is one moment. No. Yes. Sorry. Yes. The problem looks like almost hopeless, and there are some maybe more moderate problems, more feasible problems, but they also are quite difficult. Excuse me. No, yes. Yeah. So, I don't know, some problems with buttons. Okay. There is a conjecture or Bourgain from 89. that this is the conjecture about the comparison of norms in L2 and L4. And the conjecture is that, okay, the norm in L4 may be larger than the norm in L2. We can lose some logarithms, but the conjecture is that the ratio of L4 norm to L2 norm is at most some power of logarithm. Another conjecture is the conjecture by Silrole and Cordoba that if we don't take cos squares and we take some segment, and this segment is from n to n plus n to gamma, where gamma is less than 1, then the norm in L4 is can be estimated in terms of norms of in L2. Okay. So let me say again that these conjectures are open, and we will discuss mainly the last conjecture. So, Gabdulin proved the following result: that for this gamma 0, this number is 1 over the golden ratio. If we have a segment from n to n plus 10 to the power gamma 0 minus epsilon, then the norm f, the L4 norm of f can be estimated via the L norm f2, and here the coefficient is at most epsilon to minus 4. So to prove Gabdulin uses the following fact that if any non-zero number has at most k representations as a difference of two elements from B, then we have an estimate. Do you see the estimate? Excuse me. Do you see the estimate?
Yes,
Okay. This is one moment. How to? Yeah. Yes. Might be this would be better. Yes. Okay. We have this estimate. So the main part of proof of theorem 1 is to prove that any number has at most some constant divided by epsilon number of solutions to this equation. If m and n run over this segment from n to n plus n to the power gamma 0 minus epsilon. Okay. So the idea was the following: that assume that U has a representation m square minus n square. Then m plus n. Then m and m are in this segment, and m plus n also lies in a small segment. And all these numbers are divisors of the number u. And so the main point is that the number u cannot have too many divisors in this segment. Wait, this phenomenon was founded by Silleroy and Gondolin proves that for this situation we can use it, but we can expect more. One moment. Yes, we can expect more. There is the following hypothesis about the devices is that for any epsilon greater than 0, there exists some number k dependent on epsilon such that the number of divisors of number n in this segment is at most k. K depends on epsilon. Gabdulin observed that it is enough to prove this conjecture for the particular case m is square root of n. The conjecture implies the conjecture of Siller and Cordoba, and moreover, using this conjecture, we can prove the analog of conjecture of Siller of Cordoba if we replace the squares by the values of some integral polynomial, nonlinear integral polynomial. So now we say that a set A is a seed-on set, if for any u, this equation, for a non-zero u, this equation has at most one solution. Actually, we all know this notion, and from the about speculations, that it is clear that any seed-on set is lambda 4 set. It is a particular, an extreme case of lambda 4 set. And what can we say about the following, for which n dimension this number n squared, where n runs from capital N to capital N plus n, is a seed-on set. And we know something about it, that we have the following result, that if small n greater than or equal to capital N but less than this guy, n plus this guy, then this set is a seed-on set. And this result is sharp in the following sense, that we cannot replace less but less than or equal to, so there are infinitely many n such that this number, this set of n is not a seed-on set. So it is best possible in general. Yes. So let me say a few words about the example about the second part of the theorem. To prove the second part, we take n capital N is 2m squared minus 1. Then this guy is for m, and our segment has the following form: from 2m squared minus 1 plus 2m squared plus 4m plus 1. And this is not a seed-on set because we have this representation. All these guys are from this interval. Sorry. We have the following corollary, that that this set is Sidon set, but if we add epsilon, the set is not necessarily a Sidon set. Also, as for the second part of theorem 2, so I talked that there are some capital N for which the set is not a Sidon set, but also we can say that for arbitrary capital N, for any epsilon greater than 0 and for any large capital N, this set is not a Sidon set. So theorem 2 is optimal in this sense. So the set of cubes, let me turn to cubes. Gabdulin also, no, in our joint paper with Gabdulin, we proved the following, that this is a similar result, similar to result for squares, but here the exponent is 2/3. So if we have a segment whose size is at most n to 2/3 minus epsilon, then we can estimate L4 norm in terms of L2 norms. The coefficient here is at most some constant and epsilon to minus 1/4. The next theorem. Actually, theorem 4, yes. One moment. Let me see. Yes. Yes. I did not tell about this, that in the same paper we proved that something about Sidon sets, that if you take a segment of size square root of n over 2, it is a Sidon set. But if we increase the constant c and take the segment from n to capital N plus c square root of n, and c is a large constant, then sometimes for some n, this set is not a Sidon set. But in our recent papers with Garayev and Garayev, we could prove a sharp result. So if we have this segment, so we add into the capital N this guy. I'll not pronounce it, you can see it. And we can restrict inequality here, then this set is a Sidon set. But if the inequality is not strict, then for some n, this is not a Sidon set. But the situation is less understandable than for squares, because you see that corollary says that for some specific n, capital N, this set is not a Sidon set. But we don't know what happens for the most values of n, of capital N. We don't know it, and so our restriction about our knowledge about this problem is quite poor. What can we say? We can say that for any epsilon greater than 0, this is theorem 6, this set is not a set, the set is a Sedon set. So here the exponent of n is 4/7. But we don't know if the exponent is sharp. It is very probably that it is not a sharp. It is not a sharp. And from the other side, we can put the following result that if we take the exponent to third, then for large C, the set is not a Sedon set. So let me say a few words about the proofs. As for the theorem 5, I'll comment the second part of the theorem 5, where we claim that for large, for infinitely many numbers of n, we can take a segment of size square root of n such that it is not a Sedon set. How to construct this segment? We consider Peirce equation of this format, and it has infinitely many solutions. Infinitely many solutions, and if we have some solution, then we can define numbers x, y, z, t, and one can check that these numbers satisfy the equality. And actually, these numbers lie in a small interval, and so this proves the second part of theorem 5. Actually, this solubility of the equation x cubed to y cubed is z cubed plus t cubed, where x, y, z, t run over a small interval. It can be reduced to some Peirce equation, and if m is rather small, so for example, if it is close to square root of n, a little bit larger than square root of n, then we can reduce the problem to a few Peirce equations, but we know that any Peirce equation has the solutions of any Peirce equations are sparse, and so the number of n for which this set is not a Sedon set is also sparse. So this is an argument to prove theorem 6. Sorry. The proof of theorem 7 is based on the formula of Euler and Binet. So Euler constructed an infinite series of solutions to the equation, to this equation x cubed plus y cubed is z cubed plus t cubed. For some choice of parameters, we can take such x, y, z, and t, and you see that these numbers belong to a small segment, and this this gives the proof of theorem 7 with for any capital N, large capital N, we take a minimal integer greater than this guy, and then all numbers greater than but less than but this guy n plus some constant times n to 2/3 is required in theorem 7, and now we can turn to the fourth powers. So let me recall that what do we have for squares? That for sufficient large n, this segment is not a Sidon set. What do we have for cubes? For infinitely many n, not for all n, but for infinitely many, this segment is not a Sidon set. But for the fourth powers, the situation differs, and we in our last papers with graph and graph, so we proved the following result that here if we take a segment of size not square root of n, but the order of n to 3/5, then for some small c, this number is a Sidon set. The proof is elementary, but technically difficult. On the other hand, we have the following that for any positive integer n, if we take in this additive term, if you have the exponent close to 1, actually, 12 divided by 13, then this is not a Sidon set. And the proof is based on some identity. This is an identity similar to the earlier binary identity for cubes, but is the identity for quartex and there is a series of solutions to this equation for the fourth powers constructed by Euler, and in particular, so we can conclude that these numbers satisfy this equation and the line in the segment of size about n to 12, and this gives the proof of theorem. What was the number theorem? 9, yes? Yes. And the concluding remark. So what do we use for squares, cubes, and fourth powers? For cubes and fourth powers, that is, these solutions has some families of polynomial families of non-trivial solutions. I demonstrated some polynomials families for actually discovered by Euler, and the existence of some of these polynomial solutions, it is connected that this equation, if k is 3 and 4, can be obtained by consideration of some elliptic curves, and then we know that in rational elliptic curves, if we have one solution, we have infinitely many solutions. But if k is greater than 4, this technique doesn't work. So, and Erdős conjectured that the set of fifth powers is a Sidon set. Actually, there is a similar conjecture for high powers, if k is greater than 5. It's an approximation to the problem. Rouge proved the following, that if we have, instead of the set of fifth powers, we have the set of such numbers n to 5 plus integer plus the integer part of xc times n to 4, and then for some xc, this number is not a Sidon set, but he proved not for the whole number, but for the tail. So if we exclude the finite number of first elements of on this set, and then there is a Sidon set. Okay. Thank you very much.
Thank you. Are there questions for Sergei? Anyone here ever taken a 13th degree polynomial and raise it to the fourth power? No. Oh.
So,
What?
so excuse me.
No. Yeah.
What was the question?
No, it was an attempt at a joke.
Yes, but I think if you don't take polynomials, yes, actually, I can say something if you don't take polynomials. So, actually, the result that the segment of size square root of capital N is a Sidon set. It can be proven for a homogeneous class of functions. If you have, for example, a function f such that f of n is a positive integer, if n is a positive integer, and if you know that f the derivative of so if you know that the first derivative and the second derivative of f are positive, and also we have the inequality that f prime of x is at most constant times f divided by x. This is true for polynomials, but not only for polynomials. Then when it's possible to prove results similar to what we proved for squares, cubes, and quarters, that the segment of size square root of n produces a Sidon set. But yes, of course, it is. There can be interesting questions if what do we do if our function is not a polynomial function? Well, by the way, also yes, if I have some time, I'll not. I did not write it in presentation, but there is a problem. We can consider, instead of powers of n, we can consider logarithms of n. Of course, you can ask, but logarithms are not integers, okay? But we can consider e to u e to cellular. We can consider these exponents as almost periodic functions. And we can take the norm as we can take for almost periodic functions. So we have an integral from minus t to plus t and 10 to infinity, 10 t to infinity. We divide this integral by 2t and yes, divide by 2t and 10 to infinity. This is a norm, and so we can correctly define the term. If we consider the logarithm, actually this is the consideration of the Dirichlet series, the sum Cn times n to the power it. And for the Dirichlet series, we can ask this question and these questions, and so there also the situation for lambda piece property is not clear. Okay.
Sergei, thank you again.
Thank you. Thank you.
Sergey, I have a question.
Yes.
Is it known that, say, for k equals 5, there are no polynomial solutions?
There are no polynomial solutions. No. I said that it is polynomial families. Yes, you mean?
Yes.
Oh. I-
This sounds like a completely geometric question.
So-
Maybe the kind of methods that work for
Yeah,
you know,
so
ABC theorem.
I'm sorry. I'm sorry. I'm pretty sure that it is known, but I don't know about it.
So probably there are no rational curves. Yeah. Maybe even no elliptic curves. But that doesn't, of course, mean much.
Yes, it is very probably that it is known, but unfortunately,
Thank
I
you.
cannot.
Mhm.
There are over the Gaussians.
Trevor Woolley says there are over the Gaussian integers.
Oh, great.
Okay, thank you very much, Sergei.
Thank you.